In this video, we present the experimental demonstration of decentralized interaction control of a flying pararobot. The study flying pararobot, FPR, is composed of a moving platform and a number of rigid legs attached with quarters. An Aruco marker is attached under the platform, which is being detected by the onboard monocular camera to sufficiently estimate the robot pose. On the bottom of each leg, we add an LED to reduce the dependency on environmental lighting conditions. In the experiments, the FPR is controlled by a human operator with teleoperation using the estimated relative pose on each UAV. The linear velocity and yaw rate of the platform are controlled by joystick, while the robot configuration as well as the desired contact force are set by values. The first experiments demonstrate the precise positioning of the platform with real-time pose estimation by onboard cameras. The operator controls the platform to reach a tennis ball seen as a target hanging in the air and pick up the load attached below the ball. The proposed decentralized interaction controller is capable of handling the free space flight before reaching the target, as well as supporting the additional payload which corresponds to an external force about 4 Newton. Despite the difficulties of the I2 platform teleoperation, the platform has successfully picked up the load in less than 30 seconds after the takeoff in most of the repetitive tests, except one test in which the operator has failed to pick up the load in the first trial and then the flight was terminated because of the discharged batteries. In the second experiment, we demonstrate that the contact-based interaction with the environment is achievable using the vision-based pose estimation and the decentralized controller. In order to focus on the control of the interactions, we emulated a high-level perception of the environment to estimate the pose relative to the contact surface in X, Y, and yaw axis, which are then used to compute the desired velocities. The human operator can thus focus on the control of the Z-axis velocity of the platform and the desired contact force. We remark that the platform has achieved a steady contact with the board fixed in the air. In addition, we have tested the control of the robot configuration, such as by sending different values of the leg angles and the platform orientation. However, we have found that the detection failures related to the brightness changes and the marker visibility from the cameras occurred, especially with inclined platform orientation. This might be the main drawback of the proposed estimation and control of the FPR using vision-based method. However, when there is an interruption in communication, the decentralized methodology has shown its advantages. As it can be seen in the leg angle state, the communication has been interrupted where UAVs were no longer sharing their measurements, but they can still maintain their own control and land safely without crashing. This work has therefore been an encouraging step towards the application of the FPR in fully unconstrained environment.